Hi. So this is part two in my multi-degree of freedom vibrations set of videos. If you haven't seen part one, I recommend going to watch that video. I've included a link in the description for part one, as that part went through the idea of finding the mass and the stiffness matrices of a multi-degree of freedom problem. Essentially, what we see in the picture that I have on screen is that you have two masses that have two springs involved in some way, and there's a differential equation or set of differential equations that describe the motion of the masses. One differential equation for mass 1, another differential equation for mass 2. And what we did in the previous video is we found what this giant M matrix is, what this giant K matrix is, in order to store those two differential equations simultaneously inside of the matrix. The next question is, how do we solve that matrix equation? And before we jump into matrices, I want to review how we solve things in the past for a 1 degree of freedom system. So this is going to be a quick review where if I were to give you some mass that is moving with some position x, and we know that the differential equation that describes this is mx double dot plus kx is equal to 0. And the way that we were able to find the solution to this is by assuming some equation for x. And what we're going to do, there's really a bunch of ways of doing this, but for our multi-degree of freedom discussion, let's assume that x is some c e to the lambda t. And again, this is all one-dimensional, one mass, one displacement. And this is the displacement of the mass. Our goal is to figure out what the roots are, which are these lambda values in the differential or in the solution. If I take derivatives, it brings down factors of lambda. I think I have another video that goes through this and explains. But once we have those expressions for our acceleration and our position, we can plug them in. You can see I'm plugging in x double dot and x into this. And a big benefit is that these constants c will divide out, and the same thing with the exponentials will never be equal to 0. We can divide them out. So we get ultimately that m lambda squared plus k is equal to 0, and we get that lambda squared is equal to minus k over m. And that led us to have two roots. Lambda 1 is the square root of k over m, or negative k over m, sorry, negative k over m, and lambda 2 is negative the square root of negative k over m. This is the same as j omega n, and this is negative j omega n. That negative underneath the square root is the square root of negative 1. That is the imaginary number j, or I. And then the square root of k over m is omega n, the natural frequency of the system. So we had two solutions. Basically, we have some solution that is going to be c1 e to the lambda 1t plus c2 e to the lambda 2t. That is how we combine both of those solutions. And in this situation, we end up with c1 e to the j omega nt plus c2 e to the minus j omega nt. And how do we find c1 and c2 for a free vibration problem? Well, that's based on initial conditions. So I provide some initial conditions or something like that in order to find what those C1 and C2 variables are. But ultimately, that is how we get to our equation. And then, of course, if you wanted to write that in terms of sines and cosines, you can go ahead and use Euler's equation to convert e to the j omega t to cosine of omega t plus j sine omega t, and then do some trig to write it without the complex exponentials. But this is the general idea, is we assume a solution, we plug it in, and we try to find the roots. That is our goal. When we jump to multi-degree of freedom, it gets a little bit more complicated. We are still going to assume some solution like that, but we're going to assume that it is our matrix that we're assuming, not just one of the displacements. Remember, we have two displacements, x1 and x2. I'm going to write this in a very similar form to here, but I need some variable to distinguish between x1 and x2. Because if I write it as CE to the lambda t or something like that, that was meant for one mass. And I can't assume that both masses will move at the same amplitude. One might move more than the other, depending on how much they each weigh or what springs are involved. So what we do is we'll say we have some constant that's due to initial conditions, and then a vector u, which is what is called the mode shape, that will ultimately be showing us the relative ratio between the two masses' displacements, or their amplitudes. E to the j omega t. I could write that as lambda t, but just from our knowledge of a 1 degree of freedom system, we're going to leverage that here. It'll make our life a little bit easier. This U is a matrix that will contain numbers in it. For our purposes at the moment, let's just know that it's there because of the fact we have multiple displacements. In the situation earlier, we only had one mass and one displacement that we cared about. We didn't need that U. But here, this U is going to be containing information about all the masses that differentiates or distinguishes them from, distinguishes each of them from the other. So if I take the derivative of this, I will get x dot is j omega c. The derivative with respect to t will take down a factor of j omega. U e to the j omega t. And then if I do another derivative, I'll bring down another factor of j omega. The j times j gives us -1. Omega times omega is omega squared, and everything else is exactly the same. And like before, we're going to substitute in what the acceleration and the position matrices are. So this will be the same as m times negative omega squared c u e to the j omega t plus k c u e to the j omega t is equal to 0. Now, like before, we can cancel out some things. These constants are just individual numbers. We can cancel them. And the exponentials we can cancel. They're not matrices. But what I can't cancel are the u's. We can't cancel the mode shape because we can't divide by matrices. Oops, sorry. No. Division by matrices. What I can do, though, is factor it out because both terms share a u. And because matrix multiplication order matters, I have to factor out the u to the front because in this situation, the u is being multiplied on the right side of all of those other matrices. Sorry, these k's need lines underneath. Those are all matrices. because matrix multiplication order matters, I need to make sure that it's going to be negative m omega squared u, that's the order, and similarly ku, that's the order. If I put the u in the front, then that's going to be brought in an incorrect order. It has to be the correct order maintained. And this is a very important equation for us that we're going to work with. Now, this type of situation, this is what is known as an eigenvalue problem. In general, what the eigenvalue problem is saying is that if I have something like a matrix A multiplied by this mode shape U, that will be equivalent to, or if it's equal to rather, some B lambda U, where A and B are matrices, lambda are what is known as the eigenvalues. And U, for vibrations, it's the mode shape, but from an eigenvalue perspective, these are known as the eigenvectors. Now, if you look at your vibrations problem, specifically, let's say this equation up here, if we look at that equation, we can write this as Ku is equal to M omega squared U. Do we see how the A and the K are alike, the B and the M are alike, and then the lambda is like omega squared? We'll see possibly in the third video that we can solve this type of system, finding eigenvalues and eigenvectors, using the EIG function in MATLAB, where the inputs are the A and the B matrices, which for vibrations would be the K and the M matrices. But for our purposes, at the moment, we don't need this. I just want to introduce you to the terminology in that this lambda are the eigenvalues. That will be equal to omega squared. And this U is the eigenvector, and that is the mode shape of our system. And we'll explain physically what that means later. Let's go ahead and take this. We'll shrink this a little bit because I don't care that much about it, but it's there. Okay. So now I have this situation here where I have negative m omega squared plus k times u is equal to 0. And I want to find omega squared and u ultimately. So let's try to understand how this equation is true. First off, this equation can be true if u equals 0, right? If I take a matrix and multiply it by zeros, I'll get 0, which is not very exciting for us, because let's remember where that u is. That u was assumed inside of our position matrix. So if u is 0, x is 0, which implies no motion, which is trivial for us. Do we see that? If u is 0, that means that this u is 0. And then I have c e to the j omega t times 0. That means the x matrix is 0. That's no motion. That's pointless for us. Remember, that was x1 and x2 of t inside that x matrix. So if we go ahead and note this, we don't want our math to result in that. So how would we prove that u is equal to 0, which is, again, we don't want? Well, if I say to you, okay, I have some matrix, I don't know, D u is equal to 0. If I wanted u to be 0, I can't divide by d, but what I could do is multiply by the inverse of d. And d is just arbitrary. I'm just doing this as an example. I can multiply both sides by the inverse of d. And again, because matrix multiplication order matters, it'll be on the left. D inverse times d is the same as the identity matrix. That will give me u. It should not be a u, sorry. And then the inverse times 0 is 0. That's how I would mathematically prove that u is 0. But we don't want that. Because in that situation, that would mean we have no motion. So what we do is we make sure that the inverse of d does not exist. And in general, the inverse of some matrix is going to be proportional to 1 over the determinant of the original matrix. When would the inverse not exist? When that determinant is equal to 0. By forcing the determinant of d equal to 0. Because again, if this is 0, you have 1 over 0, that's undefined. That does not exist, which means we cannot multiply it to get u alone. So in our situation, we have negative m omega squared plus k u is equal to 0. This is what I was saying that whole D matrix was. If I multiply by the inverse of that matrix, that would tell me that u is 0. But we don't want that. So what we do is we say that the determinant of that matrix must be 0. This will ultimately give us non-trivial solutions, meaning we have motion. Motion is good. We want to see what's happening from a physical perspective so we can predict and estimate what these masses are going to be doing in this situation. This gives us a non-trivial solution if the determinant of that is equal to 0. So how do we find that? Well, I'm going to look at negative m omega squared plus k, and let's write that out in its entirety. From the problem we were doing last time, we saw that the M matrix was the M's along the diagonal. And then the K matrix for that specific problem had K1 plus K2 in the first element, negative K2s in the off-axis element, and then K. Omega squared distributes to those, so this is going to be negative M1 and the negative sign 2. Maybe I'll do that also. This will be negative M1 omega squared, 0, 0, negative M2 omega squared, plus K1 plus K2, minus K2, minus K2, K2. And now I have these two 2x2 matrices that we can add together. This will ultimately give me negative M1 omega squared plus K1 plus K2 minus K2 minus K2 minus M2 omega squared plus K2. This is, again, negative m omega squared plus k. And as we wrote earlier, we want the determinant of that matrix to be equal to 0, because that ensures that the inverse doesn't exist. If the inverse existed, we would end up with this trivial solution of u equals 0. We don't want the inverse to exist. So what we do is we take the determinant of this matrix and force that equal to 0. And just as a reminder, if I give you some 2x2 matrix, the determinant of that is the diagonal elements multiplied together minus the off-diagonal elements multiplied together. Only for 2 by 2. As you get to higher orders, it gets more complicated. But for our purposes, we're only going to be looking at 2 by 2 on paper. You'll have AD minus BC. So the determinant would be this term times this term. So that would be negative M1 omega squared plus K1 plus K2 negative M2 omega squared plus K2 minus BC, which would be negative K2 times negative K2. Those negatives cancel to give you a positive K2. Note that this negative sign is from the equation. The negative sign from the terms multiplied out. Oops. Okay, so now we can keep going. If I distribute the first term, I get M1, M2, omega to the fourth. If I think about this as a full term, I will get minus K1 plus K2, M2 omega squared, minus K2, M1 omega squared, plus K1 plus K2, K2, minus K2 squared. That whole thing is equal to 0. I'm going to double check that to make sure I didn't make any mistakes. If I do the first terms, I get the negatives go away, M1, M2 omega to the fourth. That seems okay. I'm going to multiply this term by this term. You get negative because of this negative sign, K2 plus K1 times M2 omega squared. That seems okay. I'm then going to multiply this one by this one. That'll be negative M1 K2 omega squared. That makes sense. Then we'll take this entire stiffness at sum and multiply by K2 to give me this. And then we subtract the K2 from before. That's still left there, the K2 squared. So let's go ahead and see if we can combine some things. M1, M2, omega to the fourth. I'll do plus. Well, I guess it could be minus. If I factor out an omega squared, this will be K1, M2 plus K2, M2 minus K2, M1. The way that I did that was, again, just distributing this M1, or sorry, this M2 to both these terms. That gives me that. Minus K2, M1 is from here, and I factored out the omega squared. Plus K1, K2, plus K2 squared minus K2 squared. Those go away. And I end up with the situation here. This is what we call the characteristic equation. And this will ultimately allow me to find omega. And we will end up with 4 omega values because we have a fourth order equation. These are the natural frequencies of the system. So if we had instances, and I'm going to do an example with numbers in a second so that we can derive some things, we can find what the omegas are given different masses or different stiffnesses. So let's do an example with numbers. Let's say I tell you that M1 is 9, M2 is 1, K1 is 24, and all these units will be nice and easy for us, no conversions that we need. And K2, I think I have is 3 units per meter in this example. So I derived the characteristic equation in a general sense, so we can just plug these numbers in now. M1 times M2 is 9 minus K1 times M2 is 24, plus K2 times M2 is 3, plus K2 times M1 is 27, plus K1 times K2 is equal to 0. This gives us 9 omega to the 4th minus, that looks like 54 omega squared, and then 24 times 3 is 72, plus 72 is equal to 0. At this point, you can use a quadratic formula to find values of omega squared. Or you can go ahead and divide by 9 and then factor. I find that to be a little bit easier in this situation. Omega to the 4th, 54 divided by 9 is 6, 72 divided by 9 is 8, equal to 0. So if we factor this, we get omega squared minus 4, omega squared minus 2. And what that means is we end up solving these equations for multiple omegas. We see here that, and I'm just going to switch the order of these, not that it matters, but just to be matching my note set that I know a lot of students have access to. I'm going to say that omega squared is equal to 2, which means that omega 1 will be the square root of 2. I'm going to say that omega 2 is equal to 2. And the frequencies that I'm missing are the negative counterparts of those. So I'm going to say omega 3 is negative square root of 2. Omega 4 is negative 2. And these are the natural frequencies of the system. In reality, only 2 of them are physical. The negative ones are needed for the total solution. If you come back up to our little review that we did before, we ended up with these 2 roots where one of them was negative. In this situation, we end up with j omega t and then negative j omega t. So even though that negative is not really a physical thing, it is required in the sense of finding the total solution. It is important. Its presence matters. But to think about a negative frequency is a little bit challenging from a physical perspective. But just note that in this situation, we do have these 4 frequencies, but we'll see that 2 of them really describe the motion. The other 2 are required, but when you see that final solution, you'll get an answer with all of them. And let's see what that actually looks like now that we're here. We said that x was equal to some c u e to the j omega t. But we had 4 solutions, so we're going to sum 4 linearly independent solutions together. So I'm going to say that the total x is going to be some c1 u1 e to the j omega 1t plus some c2 u2 e to the j omega 2t, c3 u3 e to the j omega 3t, plus some c4 u4 e to the j omega 4t. And that would be our total solution. So in this video, we found the natural frequencies omega. Those are related to the eigenvalues of the problem. In our next video, we're going to go ahead and try to find the mode shapes, which are the U values. And that will tell us a lot of information about how our system is behaving. I hope that this makes sense. If you have any questions, please let me know. Otherwise, I'll see you in the next video. Thanks. Bye.